All right. Hello and good morning. Afternoon, morning. It's still morning. To the two of us, apparently, just Jesse and I hanging out here right now. I'm sure we'll get some humans trickling in to the stream. I'm just getting everything set up. Whoa! This is huge. Oh my goodness, I'm doing this on the background too. Oh. Oh man. It's one of those mornings where one of those mornings where I pop into Photoshop to start lecturing. I'm like, who messed with my Photoshop settings? And the answer is I did. Oh, heck yeah. Yeah, we can totally. We're just kicking it right now. So for the record, Gregory, normality versus molarity is not something that I'll be testing for. I can't guarantee that your lab instructors may test you on it, whatever. But it's what normality is it is a somewhat antiquated concentration unit that still shows up. I think in engineering circles it's still used. Yes. Yeah, I noticed that the the date was wrong. I fixed it this morning. So here's normality. Normality, and this is not the official definition, but you can think of normality as what I like to call weird molarity. I think you can hear someone singing. I can hear someone singing, but I don't know if the microphone's picking it up. If you listen really closely, I think you can hear someone singing through the walls. Normality is what I just said, what I like to call weird molarity. So it's basically molarity times the number of hydrogens an acid has. All right, and you may be wondering, what do I mean by that? This is what I mean. So if you had a solution of 2.0 molar HNO3, the normality, so if we're going to switch from molar to normality, we have to multiply times the number of hydrogens in this acid. So a 2.0 molar solution of HNO3 would also be a 2.0, we call it normal solution of HNO3. All right. If you had a 2.0 molar solution of sulfuric acid, H2SO4, to convert from molarity to normality, you have to multiply by the number of H's in your acid. So a 2.0 molar solution of sulfuric acid would be a 4.0 normal solution of sulfuric acid. All right. And then, let's see. I had to adjust. Sorry, Gregory, I'm just seeing your comment. Had to adjust a pH sample of urine at work with 6 molar HCl, but all we had was 6 normal. Okay, cool. So now, okay, I'm getting excited. Now let's apply what we just learned. So if you had 6 molar HCl, to convert to normality, or let's say you had 6 normal HCl. You had 6 normal HCl. To convert from normality to molarity, we have to divide by the number of H's in your molecule, or in your acid. In this case, HCl has 1. So it turns out 6 normal HCl is 6 molar HCl. So they're the same thing, only because HCl, hydrochloric acid, only has 1 proton to donate. So anyways, it's kind of an older concentration unit. You run into it kind of in engineering circles every once in a while. Also, depending upon the supplier of the acid, some people might still measure their acid concentrations in normality as opposed to molarity. But that's the relationship between the two. Molarity says how many moles of the compound is present. Normality is asking how many moles of just H plus is present. And so if you have 2 protons in your acid, like sulfuric acid, 2 moles of sulfuric acid has 4 moles of protons. Yeah, well done. Totally. Okay, so a couple okay. My apologies. Photoshop's about to get weird. Okay, now it's not weird anymore. Okay. So a couple things of business. No worries. So a couple orders of business. You can check out the mixtape, link in the description. I really like this one. I was vibing to it this morning as I was setting up for class. Just some good, solid jams. A little on the chill side, but not too chill. You check it out, you'll know exactly what I'm talking about. Now, business-wise, so I did some soul searching, maybe, this Tuesday. Kind of looked at the oh, hey, it is, you know, we're quarantining it up here. Oh, there we go. Whoa, that's my 2-year-old, or almost 2-year-old, screaming in the background. He's rolling in on his nap. It's in 25 minutes. What was I saying? Oh yeah, I did some soul searching yesterday and realized that, including today, we only have 5 more lectures, including today. So this semester is drawing to a close. After today's lecture, there are only 4 more classes. which is crazy. But the other thing that means that means two things. The first is that exam 3 is 2 weeks away. I should say exam 3 in 2 weeks, and the final is in 3. So we've got some stuff coming down the pike. Yes, totally. That was my response as well. I wanted to be like these 3 wise monkeys. But given the amount of how last exam 2 ended up getting out late, I was talking to my wife yesterday, and she's like, yeah, you should just start working on it now. And I took her up on her advice. And so I've organized and planned the multiple choice part of exam 3, and I've written about 14% of it. I'll have more to talk about. If you want, I can talk about that a little more after lecture. So if you have questions, if you have questions about the end of all things, stay tuned after lecture, and we will talk about it. And we can get into all of it. I can tell you what I know so far, kind of give you. I'm definitely taking all of your input that you gave me on the feedback quiz to heart, and I'll talk a little bit about my process of what I'm thinking about changing, etc. after lecture. So there's a hook for you to maybe stay a little longer, or tune back in, because I realize some people have to peace out and hit up other classes. So with that little bit of advertising out of the way, let's take a look at where we are in lecture. All right. So we, you know what? We're, still talking about, VSEPR, right? Electron geometries. And, okay, here, hang on one sec. Love you. Alrighty, I'm back. Okay, so we're talking about VSEPR, and we had just introduced the trigonal bipyramidal geometry. All right, and so we're looking at the Lewis structure. We have pinning down electron groups, identifying our lone pairs, looking at our electronic geometry, our molecular geometry, and then using all of this to do two things, and that is to draw a three-dimensional representation of our molecule and to determine the bond angle. All right, and so we've got 3D, and our bond angle. So the whole goal is, like we saw yesterday, we're starting from the Lewis structure, trying to determine our three-dimensional representation and our bond angle, and the number of electron groups will determine our electronic geometry, and then the number of electron groups in conjunction with our lone pairs determines our molecular geometry. All right, and so like we said, we finished lecture on Monday talking about the trigonal bipyramid, which has 5 electron groups. Next, we're still looking at trigonal bipyramid electronic geometries, but now we're diving into seeing how these geometries change, when we start having lone pairs on our central atom. And our first example will be SH4. If you look at the Lewis structure for sulfur tetrahydride, there are 4 H's on our central atom, but there's also a lone pair. All right, sulfur's violating the octet rule, but it's fine because it's on the 3rd period. It can have an expanded octet, or go hypervalent, as they say. Now, when you look at the number of electron groups on our central atom, we have 4 atoms and 1 lone pair. Whoa! Holy moly. My pen just got huge. 4 atoms, 1 lone pair. So that gives us a total of 5 electron groups, all right? And every time you have 5 electron groups, your electronic geometry will always be trigonal bipyramidal. All right? You'll always be trigonal bipyramidal. Now, whenever you have an electronic geometry that's trigonal bipyramidal, you can start drawing the 3-dimensional representation because every trigonal bipyramid is the same. You know that you'll have 2 axial positions going straight up and straight down, and then the 3 equatorial positions are represented by 1 line that's in plane, 1 wedge, and 1 dash. So no matter what you have attached to your central atom, this will always be the scaffold that will end up. This will always be the scaffold of the 3-dimensional shape that you end up with. Now, up to this moment in time, I've always said it doesn't matter where you put your atoms, doesn't matter where you put your lone pairs. You can just put them on however you want, and it'll be fine. That is true for linear electronic geometries, trigonal planar geometries, and tetrahedral geometries, but it's not true for the trigonal bipyramid. There are actually different positions, as we learned on Monday, on this geometry. There's the axial and the equatorial. And what you need to know is when you're dealing with trigonal bipyramidal geometries, lone pairs always are axial. No, that is the opposite. They are always, lone pairs are equatorial. All right. Your lone pairs will always go to the equatorial position. As we know, they create a greater, there's more electron-electron repulsion between lone pairs. And in the axial position, your lone pairs are 90 degrees from 3 different groups. They have a little more room to breathe in the equatorial position. So you always place your lone pairs equatorial. All right. So now we need to look at our molecular geometry. We have 1 lone pair, so we know it'll be different than our electronic geometry. So let's take a look at the shape here. Again, molecular geometry does not look at the shape the electron groups make. It just looks at the shape the atoms make. So when you look at this molecular geometry, it's kind of, you can't really see it from this angle. I think you can see it a little bit better if you put it on its side. Here, hang on one second. Sophie, babe, you gotta stop yelling. You're coming right through the wall. Could you move over to the dining room table, please? Just so you don't have to think about it. So, let's do it now, please. Sophie. Okay. Holy moly, I'm sorry about that. Sometimes the family's a little extra vocal and they forget that I'm buried in a cave teaching with a fairly decent audio mic that can pick up the sounds of them yelling across the house. Okay, so this is our molecular geometry, and the name of this molecular geometry is this is called the seesaw geometry. Oops. This is the seesaw. Now, this made perfect sense to me growing up, or when I was growing up. There were these things there's this form of play equipment called a seesaw or a teeter-totter, and it kind of looked like this. If you put this molecular geometry on its side, this piece of play equipment kind of looked like this geometry, so it made sense to me. Now, this is where our age gap might come into play because they don't put these on playgrounds anymore. I think most of Generation Z, which I'm assuming most of you are, didn't grow up playing on these, unlike millennials and Gen Xers. So this is a seesaw. They don't put these on playgrounds anymore because they're incredibly dangerous. I remember at age 5, it was my first memory of a broken bone. I saw there's this kid and his sister who were playing on a seesaw, and his big sister launched him, and he flipped back, landed weird on his arm. It cracked, and I saw the bone in his arm. I saw his arm hanging and flopping at a 90-degree angle, and it was a real fun time. So anyways, if you've seen a seesaw, maybe that'll help you remember it. I will always remember it. If not, know that this is this geometry is named after a piece of play equipment that's too dangerous to put on, put anywhere anymore. But anyways, this is our seesaw geometry. This is our three-dimensional representation. Our bond angles here are still constricted. We have the axial equatorial bond angle that gets pinched a little bit down from the pure 90-degree angle because we have that lone pair. We have the equatorial bond angle, which is pinched in a little bit from its pure 120 degrees. And then also we have a third one added in. We have this axial bond angle now that we no longer have that third atom in place. And this is just a little bit bigger than 180 degrees. So those are the bond angles for... Yeah, Diana. We used to launch each other all the time with our siblings growing up. Yeah, totally sucked for his arm. So anyways, this is the seesaw geometry. It is a trigonal bipyramidal electronic geometry with one lone pair. Oh, lame. Okay. I apologize in advance. Photoshop's going to get a little wonky for a second, and then it'll be fine. Oh, well, actually, Never mind. Okay. I forgot. I meant to write in a different layer. I'm going to have to rewrite all of the things up at the top. Lewis structure. Electron groups. For real, Braj. Nobody's ever... Well, I'm sure someone's died from playing a video game. I just... it's not as... You don't get hurt as frequently. I'd say video games hurt us in different ways, maybe. Let's see. There's electron groups, lone pairs. We've got our electronic geometry. And then we have our molecular geometry. Finally, the three-dimensional representation and our bond angle, or angles in this case. Okay, now I'm going to remember to go to a different layer so I don't have to draw this. Draw this again. Here we go. All right, new layer. Okay, so that is one lone pair. Oh man, I'm getting old. I had this moment where I realized that my youngest brother, I'm 10 years older than my youngest brother, and we were looking, my kids were like, oh, let's look at the cutoff dates to the different generations and stuff, because I'm an old millennial. I was like, I just missed Generation X. And, but we were looking them up, and I realized that with the official cutoffs, that my youngest brother, who's 10 years younger than I am, is actually in the same generation as my kids. And I was like, dude, you guys, you're in the same generation as Uncle Aaron. And they were like, what? Yeah. So anyways, generations are weird. And, yep. Okay. What are we doing? We're doing a trigonal planar geometry with two lone pairs. When you draw this Lewis structure for chlorine trihydride, it'll look like this. Right, where we have our electron groups, we have 3 atoms, 2 lone pairs, so 5 electron groups, which means we are trigonal bipyramidal. Trigonal bipyramidal. Now, we can start, without looking at anything else, we can already start drawing the 3-dimensional structure, because every trigonal bipyramid has has 2 oh, that makes me feel all warm and fuzzy. Every trigonal bipyramid has 2 axial positions and 3 equatorial positions. Now, we know that the electrons, where we just learned that electrons, lone pairs, always go equatorial. All right. Now, you can put them in any equatorial position. I'm going to put them here, here, and here. Then my H's will go there and there. Now, the molecular geometry, which changes because we have 2 lone pairs, changes from the electronic geometry, will have a shape that's just determined by the atoms, by the nuclei, not by the lone pairs. So it looks like this, and the name of this geometry, if you turn it on its side, it looks like a T. This is called T-shaped. And of course, I like this one the best because my last name starts with a T. So we have a T-shaped geometry. It's a trigonal bipyramid with 2 lone pairs on our central atom. Now, our bond angles, we actually only have to worry about one set of bond angles because there are no other atoms in the equatorial position. So we just have the axial equatorial bond angle, which is pinched even harder because we have more lone pairs creating that repulsion. So there is trigonal bipyramidal geometry. All right. Now, the final trigonal bipyramidal geometry. We have, for my final example of a trigonal bipyramid, we're going to use this fun polyatomic ion, which if you draw it out, it will look like this. Each iodine in this molecule will have 3 lone pairs. So our central atom has 2 atoms attached, 3 lone pairs, so that is 5 electron groups. Whenever you have 5 electron groups, your electronic geometry is a trigonal bipyramid. And our central atom then will have 2 axial and 3 equatorial positions. Now again, we always put our electrons, as a reminder, electrons are equatorial, always. So we're going to put our 3 lone pairs in our 3 equatorial positions. Oh, sorry, I forgot my formal charge on my central iodine. And this is where I get neurotic. You always have to draw in all the lone pairs for it to be correct. Now our molecular geometry. Let's look at the shape that these make when we just consider our atoms. And when you look at the shape these atoms make, it looks just like the Lewis structure, because it is, when you have a trigonal bipyramid with 3 lone pairs, your molecular geometry is linear. We're kind of circling back to where we started. And our bond angle here is 180 degrees. You don't see the pinching because those 3 lone pairs are equally distributed around the 3 equatorial positions, so there's no kind of pushing in any direction. So we're back to linear, which is kind of nice. All right. Now, we've conquered at this point electronic geometries with 2 electron groups, 3, 4, and 5. What happens when we have 8? No, not 8. 6, because 6 comes after 5. Let's look at SH6. All right. So when you draw the Lewis structure for this molecule, it looks like this. It's sulfur with 6 hydrogens. No formal charges. We're hypervalent on sulfur, expanded octet. And we have here 6 electron groups. Whenever you have 6 electron groups, your electronic geometry is octahedral. Octahedral. And the way you draw a 3-dimensional representation of a octahedral geometry, well, there's 2 ways to do it. One way is you can draw it like this. 1, 2, straight up and down. And then on this side, a wedge and a dash. And then this side gets a wedge and a dash. This is one way to draw an octahedron. There's actually another way to draw an octahedron. They're both totally equivalent. You can actually draw 4 bonds in the plane, 1 wedge there, 1 dash there. All right, whichever is easier for you, go for it, because they're both perfectly equivalent. You can put your H's anywhere you want. And everything will be just fine. All right. We have 0 lone pairs, which means our molecular geometry is also octahedral. And the nice thing about an octahedron is the bond angles here go back to normal. It doesn't matter which you pick. There's no axial or equatorial position on an octahedron. The bond angles are 90 degrees. Now, a couple things. First, if you're wondering why the heck is this called an octahedron instead of a hexahedron, the answer is the geometric solid that's formed when you have 6 vertices, all equidistant from the center of the solid, has 8 faces. So it's called an octahedron because the geometric solid that it forms has 8 faces to it. If you, again, play D&D, you have an advantage in visualizing this over everyone else because this is an 8-sided dice. So this is what you're rolling if you're dealing damage, I believe, with like a rapier, I believe does D8 damage. So if you're a rogue and you like stabbing things with a little longer blade than a dagger, you're familiar with this geometric solid. Now, another thing to keep in mind is the 6 positions on an octahedron for atoms are all 180 degrees from each other, and I want to highlight that with some color. So this hydrogen right here in green is 180 degrees away from this hydrogen. This hydrogen, which I'm coloring in blue, is 180 degrees from this hydrogen. And finally, I'm going to use salmon to show the last pair. So all of these pairs are 180 degrees from each other. Do I need some more space? There we go. All right, so there are 3 pairs on an octahedron. Each is exact opposite, 180 degrees. So, and those, knowing those positions and that they're 180 degrees apart, will be important, not for our next geometry, but the geometry after that. All right, so let's take a look here. What happens when we have an octahedron with a lone pair on there? And for that, we're going to look at antimony, or as I like to say, the SpongeBob element, SbH5. All right, our lone pair, our Lewis structure here looks like this. All right, and we have 5 atoms, 1 lone pair. So that's, not 5. 5 atoms plus 1 lone pair, so that's 6 electron groups, which means we're dealing with an octahedral geometry. All right, and every octahedron, has the same a scaffold of a three-dimensional representation. So I'm going to draw that in now. All right. And the cool thing is, okay, so here we're going to have this basic shape. We need to place our one lone pair to see how this lone pair will affect our molecular geometry. And it doesn't matter where you place the first lone pair on an octahedral geometry. The first lone pair can go anywhere. All right, the first lone pair can go anywhere. So I'm just going to put it on the bottom there. And my other 5 hydrogens in the 5 other positions. Now, let's look at the molecular geometry. We do not look at the shape of any lone pairs to determine our molecular geometry. And when you look at the shape this makes, it makes another pyramid, a pyramidal type shape, but the base of this pyramid, you'll notice, has 4 vertices, which makes it a square. So our molecular geometry here is square pyramidal. The presence of that lone pair pinches down to our bond angle, so it's not a pure 90 degrees, just like we see whenever we add a lone pair. All right, so that is an octahedral electronic geometry with one lone pair is a square pyramidal molecular geometry. All right, now we have one last geometry to look at, and then we have all of VSEPR under our belt. All right, and for my last example, I'm going to look at, a xenon tetrafluoride. All right, we have in this structure 4 fluorines. Our central atom xenon has 2 lone pairs. So 4 atoms plus 2 lone pairs gives us 6 electron groups. So our electronic geometry here is octahedral. All right, now we can start drawing out that 3-dimensional structure. Heck yeah. Not too shabby at all. All right, so our 3-dimensional representation, for this one, I'm actually going to use the other way to draw an octahedron. All right, now, here we have 2 lone pairs, all right? And I said on the previous slide, it doesn't matter where you put your first lone pair, and that's true. You can put your first lone pair anywhere. I'm going to put mine right here. But where you put your first lone pair determines where your second lone pair goes. Your second lone pair on an octahedron will must go opposite the first. All right, the second lone pair you place must go opposite the first. So since we I put my first lone pair here, the second one needs to go 180 degrees from it. Now we add in our fluorines, and we're on our way to our molecular geometry. All right, now let's look at the shape this molecule has sans the lone pairs, where we don't consider where the lone pairs are in space. You'll notice that we've got 4 kind of vertices, right? Kind of making a square, and that every bond in this molecule is in the same plane. No bonds here on wedges or dashes. It's all flat. So this molecular geometry is called square planar. All right, and its bond angles are a perfect 90 degrees. The reason why it's 90, you may be thinking like, but what about our lone pair distortion? One of the 2 lone pairs is floating out above, and one is floating underneath. So it's got 2 set of lone pairs 180 degrees apart from each other, pushing from opposite directions, so there's no bond angle distortion in the square planar geometry. All right, and at this moment in time, so this is the conclusion of VSEPR theory, all right? So at this moment in time, oh, hang on, new slide. So now, you know all of VSEPR. All right, now you know all of VSEPR. A couple things to keep in mind. This stuff is not particularly, well, I was going to say it's not particularly hard. It is challenging for some people. It's a lot of visualization. So drawing the 3-dimensional representations can be challenging for people to learn. What you're going to be tested on, however, you're going to be tested on, can you identify from a Lewis structure? Well, you will be tested on drawing during the written exam, but in the multiple choice, I'm not going to be having you draw structures. Obviously, in the multiple choice, you're going to have to identify geometries, bond angles, etc., based on Lewis structures. So it's important that you're able to quickly identify. So these are the bullets. You want to be able to quickly identify your electron groups, electronic geometries, molecular geometries, and bond angles. From Lewis structures. All right. And that is why I recommend that you memorize this. Again, because when you're taking the multiple choice exam, which will be timed, you may not necessarily have time to look this stuff up. You kind of want to have it on the top of your head so you can just spit those out, get those questions done fast, and then give yourself more time for other questions on the exam. All right, so now you know all of VSEPR. There's one last thing you need to be able to finish exercise 5, and that is this thing called hybridization. All right, now hybridization is going to take a little bit more time to unpack, but what I'm going to do now is give you kind of the quick rundown so you can solve so you can finish that exercise and get it turned in. So hybridization, what is this thing? Now, here's the basic rundown. All right, I'm going to give you the conclusion of hybridization. All right, the final thing, very quick and user friendly. And then we're going to do this kind of in reverse order. Then what we're going to do is we're going to dig into it and unpack the why. All right, why are we? Where does this come from? What is the need? How did it develop? All that stuff. We're going to get into it. But so this is going to it's going to read a little bit like a Christopher Nolan film. I'm giving you the last scene of the movie now on hybridization, and then we're going to go back and watch the whole thing through, and then the end will make sense. All right, but here's the basic kind of idea behind hybridization. So we spend all that time looking at electron configurations, looking at quantum numbers, thinking about atomic orbitals, all that stuff. And then we started drawing Lewis structures, which involve no orbitals, just counting electrons. And then based on those Lewis structures, we started using VSEPR to analyze the Lewis structures and predict the three-dimensional shape these molecules would take. But it begs the question, what happened to the orbitals? What orbitals are involved in bonding? That's the basic question that hybridization is asking. What orbitals are involved in bonding? All right, we know orbitals are involved because orbitals hold electrons, but which ones actually engage in creating those bonds? And here's the quick answer. All right, hybridization tells you which atomic orbitals get involved in the bonding process. More or less, you'll see where the definition falls short as we unpack what hybridization is. But here's how you label hybridization. All right, here's the take home. So first, you look at the number of electron groups. All right. You look at the number of electron groups in your geometry. And then, based on that, you ask, how many orbitals do I need? All right, it's a very simple question. And based on that question, you land in your hybridization. All right. And the hybridization is what you label your central atom. So let's start with the simplest situation. If you have two electron groups, how many orbitals do you need? If you've got two electron groups around your central atom, well, you're going to use the lowest energy orbital first, right? An s orbital plus a p orbital. So your hybridization is sp. All right, that's your hybridization, the hybridization when you have 2 electron groups around your central atom. All right, what if you have 3 electron groups? Well, if you have 3 electron groups, we need to get 3 orbitals involved in bonding, right? So we're going to do one s plus a p plus a second p, right? We need 3 orbitals for our 3 electron groups. So that means our hybridization will be sp2. What happens if you have 4 electron groups? Well, we need 4 orbitals, 1s plus 3 p orbitals. That means our hybridization, when we have 4 electron groups around our central atom, will be sp3. What about 5? What would be the hybridization if you have 5 electron groups around your central atom? Well, we'd need one more orbital than sp3, right? We'd have our s orbital, our 3 p orbitals, but now we need one more orbital in the mix. What comes next? A d. So this hybridization would be sp3d. Let's do our last one. 6. All right. We're going to need one more orbital than we did with the previous scheme. So we have our s plus our 3 p orbitals, plus now we have 2 d orbitals in the mix. So the octahedron's hybridization would be labeled as sp3d2. All right? This is, in a nutshell, everything you need to solve the hybridization situation on exercise 5. Exercise 5 asks you to draw the Lewis structure, to determine the electron groups, label the geometry, bond angles, and hybridization. So hybridization comes directly from electron groups. 2 electron groups is sp hybridization. 3 electron groups, sp2. 4 is sp3. 5 is sp3d. And 6 is sp3d2. All right. Raj, great question. As it turns out, there are almost no examples in nature of, I should say almost. In nature, it's very rare to have more than 6 atoms attached to a central atom. And so you will never see more than 2 d orbitals or any f orbitals involved in hybridization. So this is as complex as it gets. Diana, you are correct. Electron groups equals atoms plus lone pairs. Yes. So the atoms plus the lone pairs. So for your hybridization, you're not looking at your molecular geometries. You're going back to the electron groups and the electronic geometry. Jesse, great question. I'm assuming you're asking about dovetailing off Raj's question. Why don't you see more d orbitals or f orbitals in hybridization? It turns out the energy from the it gets too crowded around the central atom for more things to make more bonds, because remember, the more things you put on your central atom, the more electron groups you put around there, and And so as you're adding things, the electrons in those bonds are repelling each other. And it turns out the energy gained from forming a seventh bond to a central atom is lower than the electron repulsion adding a seventh electron group would create. So that's the reason why you don't see anything above this, because adding that seventh group would crowd all the other electron groups closer together. And if it did get in there, the other ones would just push and have it pop it off, have it leave. Now, that being said, there are some rare instances of 7 things coordinated to one central atom. I believe there may even be, I feel like in grad school I saw one example of like 9 things on the center. But when that happens, the groups attached are very small. So it's possible, but only for very, very tiny atoms do you actually get enough space in there to go higher than 6 atoms on a central atom. So it's possible, but if the reason why it actually makes sense, if the reason why you can't add more than 6 things is because things get too crowded, the exception would have to be a situation where all of the individual atoms are small enough to kind of make room for maybe that 7th or 8th group. That is an excellent question. Alrighty. With this information, you now have enough to answer the question on exercise 5 about hybridization. And now that we know kind of the grand conclusion, we can dig into, okay, what is hybridization? Where did this come from? And kind of like, how did this theory of bonding develop? All right. So kind of the reason and the need. Okay, let's see. Okay, hang on 1 second. I'm looking at Raj's question. So it requires more energy to hold them if there are more than 6. Yes. So Raj, the atom would lose more energy than it gains by adding a 7th electron group. All right, so we've been on quite a saga when you think about it. When you think about the journey that we've been on, this journey of kind of exploring structure. All right, this started with a discussion of quantum numbers. Right, we had quantum numbers. And we had electron configurations. We had orbital diagrams. Right, and all of these were critical to our discussion of all 3 of these topics. Totally. So all 3 of these, quantum numbers, electron configurations, orbital diagrams, the thing that was kind of central to all of them was this was a This was orbital city, right? Orbitals were key, central, integral to all of these conversations. This was orbital city, and all of these were very atomic in nature. We were looking at individual atoms, all right? And then we made a shift from atoms, talking about atoms, to talking about molecules. Oops. All right, so we jumped from the atomic to the molecular. And in our discussion of the molecular, we talked about Lewis structures, right? We talked about VSEPR geometries. Oops. EPR, right? But in all of our discussion of Lewis theory, of VSEPR, we didn't talk about any orbitals. No orbitals at all. Question mark, exclamation point? Like, wait just a minute. Electrons are held inside orbitals. Orbitals hold electrons. How did I play a sleight of hand where I'm like, all these orbitals holding the electrons around the atom, and then let's talk about how atoms make bonds to other atoms, and let's talk about molecules. And I didn't mention orbitals at all. How did I trick you guys like that? Well, Lewis theory and VSEPR theory don't deal with orbitals at all. Not directly, especially VSEPR. VSEPR just looks at a Lewis structure and says, logically, if we're assuming these electrons repel each other, they want to get as far away from each other as they can, let's use geometry to explain it. But what about the orbitals? Where are the molecular orbitals? How do orbitals bridge this gap between the atomic and the molecular? All right, because we know they didn't go away, they didn't disappear. So where are these molecular orbitals? Turns out there's a problem. There's a problem. There is truth that you know. There is truth that you know about atomic orbitals that is in direct conflict with the truth you know about VSEPR geometries. All right. And to highlight this, I would like for a minute for us to look at methane. Let's see. I'm going to open a new slide, actually. Let's just go to a new slide rather than try to cram it in. So let's look at methane, which is the molecule CH4. Oops. So we can draw our Lewis structure here, right? And we can look at our Lewis structure, see that we have 4 electron groups around our central atom, which means that we're dealing with the tetrahedron, right? So we got every tetrahedron's the same, 2 bonds in the plane, 1 wedged, 1 dashed, and we know that we have bond angles of 109 degrees. Right? We know that from VSEPR. And I might add that this is the shape of CH4. This is the structure of the molecule. This is how it actually looks. Now, I want to draw your attention to something. Because the whole question that I raised is, where are our orbitals? What orbitals are involved in making these molecules? Well, let's look at our knowledge of the orbitals on carbon. If you write the electron configuration for carbon, it has a helium core, and then it has the electron configuration 2s2, 2p2. All right, so carbon has electrons in the s subshell and the p subshell. All right, the s subshell and the p subshell. And if you look at those orbitals, okay, now here we're gonna stretch our brains back for a while. Let's actually draw them out. All right, the s orbital is a sphere, spherical shape. All right, this is the s, our 2s orbital. Now let's look at our 3 2p orbitals. We have the pz, which is oriented along the z-axis. All right, here's our pz orbital. We have py, whose orientation is directly along the y-axis. And we have px, which is oriented along the x-axis. And I'm going to use my eraser to give it a little better, more believable shape to it. Same shape as the py and pz, is just coming directly out of the board at us. There's the px orbital. All right. So these are the 3 orbitals involved, or that carbon has, right? Or s, px, py, and pz. I'm just going to rearrange this to give myself a little more space. Now here's my question. My question for you. Based on the orientation of these orbitals, I have the following question. What angle do the p orbitals form? All right, if carbon's electrons are being held in its s orbital and its p orbitals, what possible angles do those form? Is my question. And the answer, if the p orbitals are oriented along each axis, the answer to this question is 90 degrees. My follow-up question is, what is the bond angle in methane? And that answer is 109. So how is it? It's actually going to be 90. It's actually 90 degrees. Because each p orbital is aligned with an axis. Yeah, totally. So the angle that the p orbitals themselves form are 90 degree angles, even though the p orbitals are like a straight line. So the p orbitals form 90 degree angles, but we know that the bond angle in methane is not 90 degrees. So what's going on here? Why are these two facts at odds? All right. And this is the question that chemists were asking, that physicists were asking, because they'd been able to observe bond angles, right? They knew the geometries that these molecules had, and they weren't lining up with our knowledge of atomic orbitals. And so the conclusion that they came to is that atomic orbitals were not involved in bonding. Atomic orbitals were not bonding. Because the bond angles were wrong. All right, the bond angles were wrong, and so chemists, physicists went to the drawing board and they're like, okay, what orbitals, what could possibly be happening? All right, and this is where hybridization, the idea of hybridization, came from. Remember, orbitals are probability density functions. They're mathematical functions that describe the chances of finding an electron around an atom. So what they did is, and this is the idea behind hybridization, hybridization is a mathematical averaging. It is a mathematical average of atomic orbitals all right, and it's a calculation of a new type of orbital. So what they did, when you take an average, you take the sum of the parts and divide by how many parts you have, right? So physicists, chemists took essentially the sum of the orbitals, atomic orbitals on carbon, and averaged them together. So here we have 4 atomic orbitals and when you combine these mathematically, you get 4 hybrid orbitals out the other end. These 4 atomic orbitals became 4 hybrid orbitals. All right, and those 4 new orbitals had kind of a weird shape. They were a combination of the s, 1s, and 3p orbitals. All right, we got 4 new hybrid orbitals out of this process. You'll notice that here we used px, py, and pz. All right, along with our s, our 2s orbital, we get 4 orbitals out. Because these hybrid orbitals are an average of 3p p orbitals and 1 s orbital, we say that it has, that these new orbitals have 75% what we call p character, and 25% s character. All right, that is to say that they look more like the p orbitals than the s orbital. All right, they have more p quality to them than s quality. And now, so we took an average of our 4 orbitals. We got 4 new mathematical functions out. And when you look at where these 4 new orbitals, sit on a 3-dimensional coordinate plane, these are the positions they occupy. Now, we know that the s orbital has no directionality to it, but these new hybrid orbitals are a combination of the s with px, py, and pz. So the distribution, or the way these orbitals are pointing, are going to be distributed across all 3 dimensions because they inherit their directionality from px, py, and pz. The first of these hybrid orbitals is oriented along the z-axis. The second is in the zy plane, kind of angled down. The third comes out at you, and then the fourth goes back behind, kind of like a wedge and a dash. And when you measure, so if you put a carbon atom at the center here, I'm going to change my color. If you put a carbon atom at the center and you measure the angle formed by running an axis directly through any 2 of these new hybrid orbitals, the angle formed there is 109. All right. And so with hybridization, we were able to predict the tetrahedral geometry by taking an average of the 4 atomic orbitals carbon has access to and mathematically averaging them into these new hybrid orbitals. All right. Which, by the way, these have a name, and they are called sp3 hybrid orbitals. We say that the carbon in methane is sp3 hybridized in order to form its bonds with its 4 hydrogens and make that molecule of CH4. Cool? Okay. How's our time looking? Okay. Now, let's talk about what's going down here. And we'll continue with this discussion on Wednesday, but let's close out our discussion with methane. So let's look at our sp3 hybridized carbon. All right. It has that's a ugly sp3 hybrid orbital. It's slightly better. Let's talk about how it makes its bonds with hydrogen. All right. Now, carbon has 4 valence electrons, right? it has 4 valence electrons, and it's going to have 1 in each of its sp3 hybrid orbitals. All right, let's talk about how carbon actually forms. What orbitals are involved with forming the bonds between the carbon central atom and the hydrogen atoms attached. All right, so this is our sp3 hybridized carbon. Now let's bring in our hydrogen to the mix. Now when you look at hydrogen's electron configuration is 1s1. All right, it has a 1 electron that's being held in a 1s orbital. All right, and as we know, hydrogen wants to have access to 2 electrons. That way it has the same electron configuration as its nearest noble gas, helium. And what hydrogen does is it brings its 1s orbital into direct contact with one of carbon's sp3 hybrid orbitals, and it overlaps its 1s orbital with one of carbon's sp3 hybrids to create that bond. You'll notice here that both the electron, that the hydrogen, when it does this, its s orbital eclipses carbon's 1 electron in this sp3 hybrid orbital. So now hydrogen feels like it has 2 electrons in its orbital, and carbon, because of the eclipse between carbon's sp3 hybrid and hydrogen's 1s orbital, carbon has access to hydrogen's electron, so it feels like it has 2 electrons in this orbital, and that is how a bond is formed. All right, this is called constructive orbital overlap. And it is how so this is constructive orbital overlap. The type of bond made through constructive orbital overlap is known as a sigma bond. All right, so this is known as a sigma bond created through constructive orbital overlap. 2 electrons smashed between 2 nuclei. That is a sigma bond. All right. Now, carbon has just made 1 bond to hydrogen. That hydrogen's content. Carbon's still looking to make 3 more bonds. So to form our molecule of methane, we need to bring in 4 more hydrogens, each engaging in constructive orbital overlap to form a sigma bond. Now, there's more than one type of constructive orbital overlap. Sigma bonds are formed through what's known as direct overlap. All right, direct overlap, as we have here, forms a sigma bond. All right, and so in this molecule, if I were to ask you how many sigma bonds are in this molecule, we would say that CH4 has 4 sigma bonds, because all the bonds in this molecule are created through direct orbital overlap between carbon and hydrogen. Cool? All right. This is where I'm going to end lecture today. We will pick up next Monday with more hybridization. We'll get into it. Okay. So we'll continue our discussion with hybridization. This is we've covered today sp3 hybridization. On Monday, we'll also look at SP2 and SP hybridization. We'll see that there's more than one type of constructive orbital overlap. It is a lot of stuff. Raj, you're totally correct. We'll see that a new type of constructive orbital overlap. We'll see how pi bonds form through something called indirect overlap. It'll be a lot of fun. It's actually probably my favorite part of the course. So this is like eating dessert right at the end. So I know some of you guys are going to run to other classes. I did want to say a quick word. I'm down if you guys have any questions, stuff that you want to get addressed. Totally down to hang and talk about this about that. But I wanted to say a quick blurb about exam business. So as I said at the beginning of our live cast, I started working on the on exam 3 yesterday, specifically the multiple choice, because the multiple choice on exam 2 I got the most feedback on. Everybody pretty much felt that the take-home exam was somewhere in between hard to doable, but was more or less fine. And I think that was because from the feedback that I got was that you had like 36 hours to do it, so there wasn't that time crunch. Even though the problems were hard, you could sit down, you could work through them, you could figure them out, and I didn't really get any complaints about the written exam, but I got a lot of feedback about the multiple choice, and how it was hard, and the feedback was consistent there as well. It was that it wasn't the feedback that you guys gave me is not so much that the problems themselves were impossible to do, but in the amount of time given, that it was hard to get everything done. And so what made it difficult was the time crunch. So as far as, with this round, I kind of spent yesterday kind of brainstorming, thinking, okay, how should we do things differently on the multiple choice for exam 3? And, because it's I've got to walk this kind of tightrope, because it still should be a challenge, but I feel like the challenge should be toned down so it's not quite as intense as the second one. So and really this is the challenge. For me, how do I make it not as intense but still challenging? Because I don't want to give you guys something that's easy that doesn't challenge you to think and all that stuff. So I don't want to swing too far in the opposite direction where it's not a challenge for you, because this is a college chemistry class. It should be challenging, but how do we tone it down without making it a giveaway multiple choice? And as I was thinking about the multiple choice exam, and again, this is still stuff that I'm working through. I haven't landed for sure on one thing or another, but as I was kind of deconstructing, breaking it down, I kind of thought there are 3 different parameters that can be modified to make things easier. One is the obvious one, right? There could be more time, right? Is a door number 1. More time. If I had, if more time was available, that would obviously make it easier. Another thing that could soften it would be fewer questions. which is really just another way of saying more time, because if I keep the time the same but put fewer questions on it, you'll have more time per question. And then the third way to soften it is by putting simpler questions on the multiple choice exam. All right. So if it was the same number of questions with the same amount of time, but the questions didn't take as long each, that would be another way of kind of making it more doable. So these are kind of the three things. So these are the parameters that I will consider modifying. And I wanted to kind of give you a glimpse into my thought process, because I'm not sure which kind of avenue I'm going to go down. But for example, if I picked door number 3. For example, if I decided to go with simpler questions, and then you guys logged on and you're like, what? It's still 30 questions with 50 minutes. He didn't listen to us. I didn't want you to be like shocked or think that I didn't care. If it's the same number of questions and the same amount of time, then I guarantee you that the problems that I've put on there are a step below the problems that were on exam 2 multiple choice. So I didn't want you to think that I was callous or careless. And I'm not saying that I'm definitely going with simpler questions. I could go with the same caliber question, maybe do less of them, or maybe I do the same caliber questions but then extend the time. I'm really still kind of figuring it out. And also, I'm writing the questions now. So I'm also in the process of forming them. So part of it will also be, I'm going to write all the questions. Again, I put out a pretty extensive question bank. And so I'm writing the questions, I'm getting that all online. And then once I have those written up, it'll take me kind of taking a step back and going, okay, how hard are these? Are these about the same as the last exam? If they are, should I put fewer of them on there or give them more time? Or are these easier questions? And, so anyways, hopefully that kind of gives you a glimpse into how my brain is kind of working, processing this stuff. As of this morning, the exam 3 multiple choice is 14% complete. So I've written 14% of the problem bank at this moment in time. So as this number gets higher, I'll obviously have more answers to specific questions. I haven't even cracked into the final, which, yeah, I'm still kind of going back and forth. The final might be 100% through Canvas. I'm not sure. We'll see. But anyways, I don't know if you guys have any thoughts, questions, comments. I'm totally down to hang, talk about them, answer them. But that's all I have, and this is the exam announcement that I mentioned at the beginning of class. That I said I would talk about more at the end. This is that thing. So yeah. If you don't have any questions on what is it? Monday, we'll continue our discussion of hybridization. We'll get to actually dig into the meat of SP2 and SP hybridization, which plug for those of you who have to take 420 and 421. that is the closest we get in Gen Chem to the living, beating heart of organic chemistry, is what we're about to dive into with SP2, SP, and you've already seen today, SP3, hybridization. That is the stuff that if you do have to take organic chemistry, you'll want to review and be comfortable with before moving into the next class, because it'll be assumed that you remember it, but the reality is there's a whole semester of Gen Chem 401 between you and 420, so it would be a good idea to go back and brush things off, dust off the cobwebs. All right, so I think I'm going to go ahead and call that a stream, a lecture. Thanks everybody for joining in live. Hello, and thank you to everybody who is going to be watching later at your leisure. We only have 4 more of these to do, and then we're done. Drop by on Friday at 1:30 for office hours, if you're so inclined. If you can't make it, send in an email, and your question will be answered. All right, dudes, I hope you have an awesome Wednesday and a righteous Thursday. Yeah, heck yeah. Of course. You are welcome. You guys are far and away the most fun class I've ever had with Gen Chem. I'm saddened that it's half of it has been digital, but then part of me wonders if this is why it's been so fun. Anyways, who knows? Have I considered a different format for the multiple choice? Let's see. Okay, Jesse, great question. By different formats. Okay, gotcha. Other than Canvas. I have not. I have not. Yeah. Multiple choice. Will totally be hosted by Canvas. Will totally be hosted by Canvas. Mostly because it integrates seamlessly into the gradebook. Yeah. So multiple choice will definitely be held through Canvas. Also, and it integrates with the gradebook. It also the problem banks that I've written or wrote for the first exam and writing for the second exam will be in Canvas. So I'll have access to those to change them, tweak them, add to them, perfect them in future semesters. So it just kind of creates this continuity between this class and future classes, and the ability to update and optimize, because Canvas won't change. I mean, Canvas gets updates and stuff, but Canvas will continue to be the education site platform that Folsom Lake College uses, and so it'll have it kind of has this built-in future compatibility with classes that I'll teach. So it'll definitely be hosted through Canvas, and but the specific parameters, as I was talking about on this slide, whether it's more time, less questions, simpler questions, that will definitely be tweaked for the exam 3 multiple choice. Totally, Jesse, great question. I haven't considered it, mostly for those reasons. Gradebook integration, Canvas is what FLC uses for site hosting, and things have changed actually. Given what we've all gone through, use of Canvas used to be 100% optional for faculty. It was at their discretion to either use it or not use it, if you can believe it. But now, at least starting in the summer, there's been a change where we're actually required to use Canvas now. Obviously, summer's going to be 100% online, but also in the future, we don't know what the COVID pandemic is going to look like, when it'll show up again, when we'll hit a second wave or a third wave. So we're now required to use Canvas in case things have to go 100% online again. So anyways, yeah. I think that's the end. Unless you guys have more questions, obviously, I'm totally down to hang. If you don't, then we'll conclude the stream here. I'm gonna hop off, timestamp this video, get the PDFs uploaded for those of you who use them, and catch some of you in office hours on Friday, and then the rest of you up on here for Monday's lecture. Thank you guys. Catch you later.